welcome you all in this lecture of the heat equation. Today I am going to solve those problems of the heat equation in which the temperature at the end points of the bar is non-zero in steady state condition and then it reduces to zero in unsteady state condition. So these problem belongs to the particular type, say type 2 of the problem, in which temperature at end points, in which the temperature at ends is non-zero in steady state condition and is 0 degree centigrade in unsteady state condition. So here we are going to solve those problems in which the temperature at ends is non-zero in steady state and it is 0 in unsteady state. So if consider the one-dimensional heat equation, del T upon del T equal to C square, or say K del T upon del T2 del T upon del X2. Now in steady state, your del U upon del T will be 0, therefore del T upon del X2 equal to 0, or you can say that on integration your U will be C1x plus C2. Now if temperature at the beginning point of the bar is θ1, say at A, if the temperature at A is θ1, then the left hand side will be θ1. Now at A your x will be 0, so your C2 equal to θ2. So your C2 equal to θ1. If temperature at B, where your length of the bar is L, you know that say this is your point A, this is your point B. Here you know that the length of the rod will be 0 and say the length of the bar at this point is L. So at B, if the temperature is θ2, then your length of the bar will be L plus C2. Now C2 is θ1, so your C1 will be θ2 minus θ1 divided by C1 and divided by L. So this is your C1. Therefore, hence in steady state condition, your temperature will be as you know that here your temperature does not depend on time, so this is your 0. So in this case your temperature will be C1. C1 is θ2 minus θ1 upon L into x plus C2. C2 was θ1. So this is your temperature when your end A and B has temperature θ1 and θ2. So this will be your temperature at any point when your time is t second. So this is your temperature of the rod in steady state condition. Now let us assume that now the temperature reduces to 0 at both A and B. So now we will discuss the unsteady state condition when your temperature at the end point is 0, and it is similar to the previous type, that is type 1, when your ends are at 0 degree centigrade. So let us solve a problem of this type where the temperature at end points is non-zero in steady state condition and it is 0 in your unsteady state condition. Question: a rod of length say 30 centimeter has ends A and B at temperature 20 degrees centigrade and 80 degrees centigrade respectively. So the rod has length at 30 centimeter and temperature at the point A and B are 20 degrees centigrade and 80 degrees centigrade respectively until the steady state condition prevails. So this is your temperature until your steady state condition prevails. Now let us assume that the temperature at A and B are reduced to 0 degrees centigrade. So the temperature at each point is then the temperature at each point is then suddenly reduced to 0 degrees centigrade. So, and kept so. And kept so. So, find the subsequent temperature at any point and at any time. So that means we have to calculate UXT. Solution. Here you can see that rod has length 30 centimeter and temperature at A and B is 20 degrees centigrade and 80 degrees centigrade respectively. So in steady state condition, we know that our U is theta 2 minus theta 1 upon L into x plus theta 1. So this is your temperature in steady state condition. So therefore here your UXT will be theta 2 is 80 degrees centigrade minus theta 1 that is 20. So this will be your 60 divided by length that is your 30 centimeter plus x plus theta 1. Theta 1 is 20 degrees centigrade. So this will be your 2x plus 20. So this is your initial temperature when the rod has temperature at 20 degrees centigrade and 80 degrees centigrade in your steady state condition. So now this is your initial temperature. Now suddenly temperature at A and B are reduced to 0 degrees centigrade. So now on steady state condition, that means when your temperature are reduced to 0 degrees centigrade with change in time. So in unsteady state condition, the solution of heat equation will be this. The solution will be UXT equal to your e to the power minus k lambda square t into C1 cos lambda x plus C2 sin lambda x. So this will be your solution in an steady state condition where the boundary condition are when the length of the rod is 0, that means at A your temperature is 0 degree centigrade. When the length of the rod is 30 centimeter, when the length of the rod is 30, again your temperature is 0, and then your initial temperature, that means when initially your condition was steady state, so your initial temperature will be 2x plus 20. This is your steady state condition. That means when your temperature does not depend on the time. So Ux, that means temperature is 0. So your initial temperature will be 2x plus 20. Now using these three boundary conditions, we will solve this heat equation. We will solve this solution of the, we will find out the constants C1 and C2. Now using first, if your x is 0, using 1, when your x is 0, your temperature is 0, so this will be your C2 is 0, so we will have k lambda square t. Now because x is 0, so this will be cos 0 is 1, so from here you can see that our C1 will be 0. So now C1 is 0, so our solution will be e to the power minus k lambda square t into C2 sin lambda x. Now using the condition 2, using boundary condition second. So that means when your length of the rod is 30 and the temperature at the point B is 0 degree. So now if you put x equal to 30, then again the left hand side is 0, C1 is already 0, so we will have C2 sin 30 lambda equal to 0. Therefore, 0 equal to e to the power minus k lambda square t, C1 is already 0, so C2 sin lambda x, so 30 lambda. So this is equal to 0. Now C2 cannot be 0, otherwise your temperature will be 0. So from here you can see that your sin 30 lambda equal to 0, and 0 means sin n pi. So that means your lambda is equal to n pi upon 30. So this is your lambda. Now we have the value of C1 and lambda. So your solution is uxt equal to e to the power minus k lambda square t into C2 sin lambda x, and general solution will be uxt equal to summation n equal to 1 to infinity your Cn e to the power minus k lambda square t into sin lambda x, and we have the value of lambda as n pi upon 30. This is your lambda. Now let us use the condition number 3 using boundary condition 3 to get the value of C1, Cn. So using boundary condition 3, that means when your time is 0, the initial temperature is 2x plus 20. So in the left hand side we will have 2x plus 20, and in the right hand side your t is 0, so e to the power 0 is 1. So we have Cn sin lambda x. Now here you can see that the right hand side is your half range sine series. In case of half range sine series, the Fourier coefficient Cn is equal to 2 upon L, 0 to L, fx into sine, and your lambda was n pi upon 30. So this will be your n pi x upon 30. So in case of half range sine series, your fx, your Cn will be 2 upon L, 0 to L, fx sin n pi x upon L. Here you can see that your length of the rod is 30, so this will be your 30, and here we will have 30. So this is your Cn, 2 upon L, 0 to L, fx sin n pi x upon L dx. Now the value of fx is 2x plus 20. So this is equal to 1 upon 50, 0 to 30, 2x plus 20 into sin n pi x upon 30 dx. Now let us integrate this term. So on integration, we have 1 upon 50. Now 2x plus 20, integration of sine will be your cos minus cos n pi x upon 30 into 30 upon n pi. Then we will have minus sign, and the differentiation of 2x will be 2, and again the integration of this bracket will be sine n pi x upon 30 into 30 square upon n square pi square, and the limits from 0 to 30. Now here again you can see that on putting x equal to 30, this will be your sine n pi, which is your 0. Again for the lower limit it is 0. So this term is 0 for the both upper and lower limit. Now coming to this term. Now if your x is 30, then your upper limit will be, if your x is 30, then you can say that this will be your 80. Now if your x is 30, then this will be your cos n pi, and cos n pi is minus 1 power n. So we will have minus 1 power n into 30 upon n pi. Now if your x is 0, then this will be your 20, and this will be your minus minus plus, so 20. If your x is 0, so that means cos 0 is 1, and we have 30 upon n pi. So from here you can see that your 30 upon n pi is common, and again 20 is common. So we will have 600 divided by 15 equal to 4 times minus 1 power n plus 1 plus 1. So this is equal to n divided by n pi. So this is equal to 40 upon n pi into 4 times minus 1 power n plus 1 plus 1. So this is the value of the coefficient Cn. Yes, 40 upon n pi, and then 1 plus 4 minus 1 power n plus 1. So your solution will be, therefore, hence your solution is, your solution will be n equal to 1 to infinity. Let us put the value of Cn as 40 upon n pi into 1 plus 4 minus 1 power n plus 1, then e power minus k, lambda square, lambda was n square pi square upon 30 whole square, that means 900 into sin n pi upon 30x. So this is your solution of the problem. So this is your solution of the problem when your ends are at initially at 20 degrees centigrade and 80 degrees centigrade, and then cooled at 0 degrees centigrade. So this is our solution. Now let us solve one more question of this type. Question number 2. Suppose that a rod of length L has ends at temperature 0 degree centigrade and 100 degree centigrade until the steady state condition prevails. Now suppose that suddenly the ends are cooled to 0 degree centigrade and kept at this temperature. Now find your temperature uxt for any time and at any point. So solution, this is similar to the previous question. Here you can see that in my previous question the initial temperature was 20 degrees centigrade and 80 degrees centigrade. Now in place of 20 we have 0 and in place of 80 we have 100 degrees centigrade. So here your in steady state condition our uxt will be theta 2 minus theta 1 upon theta 1 into x plus theta 1. Here we have L. So theta 2 means 100 minus 0, that means 100 minus 0 upon length of the rod into x plus initial temperature, that is 0. So this is your 100x upon L. So this is our initial temperature. Now the temperature of the ends are reduced to 0 degree centigrade. So in transient state, or you can say that now solution of the heat equation when ends are at 0 degree centigrade with uxt equal to e to the power minus k lambda square t into c1 cos lambda x plus c2 sin lambda x. So here you can see that the boundary condition are first condition is when your length of the rod is 0, that means at point A your temperature is 0 degree centigrade. When again the length of the rod is L, your temperature is again 0 degree centigrade because ends are cooled at 0 degree centigrade. And then the initial temperature is equal to 100x upon L. So now using these three boundary conditions, let us solve this problem. So using the first boundary condition, that means when your length of the rod, that means at point A where your L is 0 and temperature is 0. So if your x is 0, then we will have sin 0 here and C1 into cos 0 is 1. So this will be 1. That means C1 will be 0. Again, using the second boundary condition, that means when your length of the rod is L and temperature is 0. So in this case, we will have C2 into sin lambda L. Again, C2 cannot be 0, otherwise our whole solution will be 0. So from here, our sin lambda L will be 0 and this is your sin n pi. So lambda will be n pi upon L. So that means our solution is uxt equal to the general solution as in previous question. This will be your Cn e to the power minus lambda k square t into sin lambda x, where our lambda is n pi upon L. Now let us use the third boundary condition, that means using when your initial temperature is 100x upon L. Then from here we will have 0 equal to, when your temperature is, when your time is 0, that means e to the power 0, that will be your 1, and in the right hand side we will have Cn sin lambda x, lambda was n pi upon L, so this will be n pi x upon L. Now again you can see that in the right hand side we have half range sine series, so your Fourier coefficient will be 2 upon L, 0 to L, 100x upon L into sin n pi x upon L into dx. So from here we will have 200 upon L square and the integration of x into sin n pi x upon L. So integration of sin will be minus cos into L upon n pi, then differentiation of x will be 1 and the integration of cos will be sin n pi x upon L into L upon n pi. So this will be L square n square pi square and the limits 0 to L. Now here you can see that if your x is L, then we will have sin n pi, that is 0, and at x equal to 0 it is again 0. And at here for the upper limit we will have this one as L, so this L square and L square will get cancelled, and for x equal to L this will be your cos n pi, so we will have 200 upon n pi into minus 1 to the power n plus 1, because you can see that at x equal to L this will be your L into L, that means L square will get cancelled and we will have minus cos n pi. Cos n pi is minus 1 to the power n, so we will have this one as answer. Therefore our solution will be, solution is uxt equal to n equal to 1 to infinity into Cn, Cn is 200 upon n pi minus 1 to the power n plus 1 into e to the power minus lambda, lambda was minus k lambda square t, This was your k lambda square t. So it was minus k lambda square. Lambda square means n square pi square upon l square into t into your sine lambda x. That means sine lambda means n pi upon l. So this is our solution of the present problem.